We're going to look at multi-stage experiments, and we're going to use tree diagrams to examine these. You can read a lot of textbooks and they have tons of probability rules and they can all get confusing. So the more we can actually model what's happening, the easier it is to understand these rules. So we're going to start out with that. So we have a definition. An experiment that consists of more than one step is called a multi-stage experiment. And each step in the experiment is referred to as a stage. So let's review the fundamental counting principle. If I have different events, A sub 1, A sub 2, through A sub n, that can occur each of these number of ways, M sub 1, A sub 2 can occur in M sub 2 ways, and so forth, then the number of ways that A1 followed by A2 and so forth can happen we find by multiplying the probabilities together. So one of the ways to show the possible outcomes in a multi-stage experiment is to use a tree diagram. The first set of branches are the possible outcomes from the first stage. The second set of branches are for the second stage, and then you can build onto that and keep branching out. So for example, suppose we have a spinner with the letters A and B, and a four-sided die. Our experiment will consist of spinning the spinner, then tossing the die, and recording the results. What would the tree diagram look like? So first, we're going to list the possible outcomes for the first stage, like branches on a tree. So I could either spin the A or I could spin the B. Now that I have that, from each of these branches, I'm going to make branches for the outcomes of the second stage. So I could get a 1, 2, 3, or 4 on these dies after I spun an A, or I could spin a B and get either a 1, 2, 3, or 4. So we have all the possible outcomes here from the sample space. So you can read across to see the possible outcomes, and again, here's the sample space. Okay, and we should have 8 possible outcomes. I left the word 8 out here. For the experiment, since there are 2 outcomes for stage 1, 4 outcomes for stage 2, so we find the total number of outcomes by multiplying those together to get 8. Now if I assign the probabilities for each outcome as I'm drawing my tree diagram, I get a probability tree diagram. So at my first set of branches, the A and the B, it was a spinner which was divided in half. Half of it was A, so there's a 1/2 probability you spin the A, 1/2 probability you spin the B. And then assuming that the four-sided die was fair, each of my outcomes, I have 1/4 is the probability for each of those. So 1/4 probability that I get a 1, 1/4 probability that I get a 2, 1/4 probability that I get a 3, and so forth. In this case, we are conducting a multi-stage experiment where neither of the outcomes affects the probability of the other. what I spin on the spinner doesn't affect what I get on the die. And these events are called independent of one another. So if I have independent events, then I find the probability of the first one and the second one happening by multiplying them together. What I like about tree diagrams are that the events along each branch are mutually exclusive. So to find A or B, we simply need to find those probabilities and add them together. So now we have our tree diagram we just drew. So now I can look at the probabilities. Probability of A1 spinning an A, rolling a 1 is 1/2 times 1/4. So I just read along the branch. And then a a 2, that's 1/8. And all the way down, these all turn out to be 1/8. So suppose we look at a different example. We have this jar and it contains 2 black marbles and a red marble. So we're going to draw a marble from the jar, and then we'll put the marble back in and make a second draw. So we want to look at 2 probabilities here. What is the probability that both marbles are black? And what is the probability that at least one was black? So let's look at the tree diagram and determine those answers. Now, the probability of black is 2 out of 3 on the first draw because there are 2 blacks out of 3 marbles. Now, since the marble is returned, then the probability in the second draw is no different. I still have the same set of marbles I'm drawing. Also, the probability of red remains the same on each trial because I'm going to pull the marble out and put it back in. This is called an experiment with replacement. With replacement, we are going to have independent events because the probability doesn't change from trial to trial. So now we pull a marble out of the jar and it's either black or it's red. Now remember, 2 of those marbles were black, so 2/3 is the probability I get a black. 1/3 is the probability I get a red. I'm going to put that marble back in. So again, my jar still looks the same. I have 2 reds, 2 blacks, and a red again. So then on my second draw, after I draw black, I could either draw another black or I could draw red. The probability again is 2/3 and 1/3 because they haven't changed. And then if I draw red first, then the probability of black is 2/3 and the probability of red is 1/3. So I can find the probability of black by multiplying the 2/3 times 2/3. Black red by multiplying 2/3 times 1/3 to get 2/9. 1/3 times 2/3 for red black. And then 1/3 times 1/3 for red. So I've drawn my little jar here, but the probability that both are black only happens on this branch. So that would be 4/9. The probability that we only get, or that we get one black, it doesn't mean we only get one black, but we get at least one black. This branch has a black, this branch has a black, and this branch has a black. So when I add sorry, I should have gone around like that. These, where they're actually blacks, I can just add those together and I get 8 out of 9. So that's the probability I get at least a black, one black. Now let's change the experiment. This time we're not going to replace the marble before we draw a second marble. So what we want to find is what's the probability that both marbles are black. We have the same jar. We're just not going to replace the marble after we draw it. So drawing a black on the first draw is 2 out of 3. But on the second draw, because we leave that black first marble we draw, we leave it out, now there's only one red and one black in the jar. And the probability of drawing a black there is 1/2. Now the probability of selecting a red on the first draw is 1/3. But if I pull that 1/3, that red out, I'm left with no reds left. No reds out of 2 marbles. And so that probability is 0. So let's look at the tree diagram. Now you will have probabilities in different problems. You know, these numbers will change according to whatever problem you're looking at, but the method is still the same. So again, on the first draw, I have 2 out of 3 that are black, 1 out of 3 that are red. Now because I'm looking at non-independent events, I take care of the fact that they're not independent because I change the probabilities on the tree. So now, if I draw black the first time, I only have 2 marbles left, and the probability that one of those is black is 1/2, and that one of those is red is 1/2. If I draw a red on the first draw, then I have 2 marbles left, and 2 of those 2 marbles are black, but none of those are red. So if I want to find each of the probabilities, so the probability of getting black is 2/6. So I'll write the probability of black. The probability of getting a black red is 2/3 times 1/2, which is also 2/6. The probability of getting a red and then a black would be 1/3 times 2/2, which is 2/6. It's 1/3, but I'm leaving it all in sixths. And then finally, the probability of getting a red is impossible, right? There's not even 2 reds in there. And I wanted to do this to show you that when you have all your probabilities, they should all add up to be 1. So now let's look at the probability. The probability that I get both black only happens here. So I just look at this branch to tell. Probability I get 1 black. Okay, that happened. I've got a black here. Okay, so unless it says only 1 black, you can assume that as long as you get a black, it's part of the answer. I've got a black here. I've got a black here. So if I add the 2/6, the 2/6, and the 2/6, I'm going to get 1. So it's 100% probability that I'll get at least 1 black.